The agenda of part 2 is that we will continue with technology and services. And then we will have a session with Nordic Tour. It's inside the field readiness for automation. And then we go over to short-range communication services and future perspective. And that will end the showcase. So I will now leave the hand to Kenneth Sørensen, that is tell us about services, weather and road condition, and slow and stationary vehicle.
My name is Kenneth Sørensen. I am an NPRA employee since February. Last year I was a consultant for the NordicWay project, where I mainly did the coordinating of the tests on E8 in Skibotndalen. So I'm going to talk about two of the services that I was most involved with. It was weather conditions and the detection of slow and stationary vehicles. So first I will talk about the weather conditions. We used mainly two sources. We used NPRA weather reports from stations in the area, quite close to the area, and Triona had set up two stations with weather sensors. One at Lullemoen, which is at the entrance of the valley, quite far from the Finnish border, and one at Gardermobakken, which is quite close to the Finnish border. The NPRA report are still being collected by the test system. Triona's data is not longer collected, but it's available through the ITS platform. So this is the drawing for the reporting that we used. I was mainly involved with the two layers, the application backend system and roadside systems. So this is the architecture that we plan to implement. We had sensors. This doesn't show the NPRA data source. It only shows the Triona data source. We had sensors on the roadside doing measurements, and the measurements were periodically collected by Triona. And the data was made available for us for evaluation and for notification. We intended to send the weather data to the Interchange. Unfortunately, the coronavirus hit us before we got to test that, so that hasn't been implemented. Those tests were cancelled. So currently the only way we have of notifying users about road conditions are using the variable message signs. So just, our back system is called Andeby. That's the application server, which is collecting the data, storing data, and displaying data for operators. Just to clarify, the next slide talks about that. The backend system was implemented in a platform called Node-RED. It's a platform for rapid prototyping. It's drag and drop programming. It makes it quite easy to make nice looking applications and have the functionality up and running quite quickly. It's not very suited for operational duties, but it's very good as a prototype platform. The weather data is received from the NPRA over a REST API that we made ourselves to make it easy for different services to use it. And Triona supplied us with data using a message server called MQTT. It's a very common communication technology for IoT system, and this has some IoT characteristics. Through the system, operator could look at the values coming in, evaluate them, and push some messages to the variable message signs. We had some predefined messages. High winds, put on chains, which is for slippery conditions, either ice or a lot of snow. and just a general sign that was showed all the time, which read something like "drive carefully," and one of the signs had just a sign of the wind speed. The signs are set using an API in Trionos ITS platform, so it's possible to automate setting the signs. But we did not automate this, and I will get back to why we didn't do that. So basically the communication flow is from the weather stations either to Trionos ITS platform on their chosen protocol, and from the weather stations to Andeby, our application server. The user can look at the different applications there, evaluate the situation, and instruct the system to set the value on the signs. So this is what the application looked like. We have a field for temperatures, we have air temperature, road temperature, and the dew point. They are all color coded, so blue here would mean freezing conditions. We had a friction measurement. There was an optical friction measurement. So 0.2 would be fairly low. And we also had the wind directions. So this had to be monitored by an operator. There are 3 different variable message signs in the area. There is one at Lullemoen, which is at the end furthest from Finland. The data is visible for vehicles driving towards Finland. There's one at Helligskogen, which is pretty much halfway between Lullemoen and Garderborgbakken, which is the area where some of the tests were done, which also is only visible for vehicles coming towards Finland, and Perskogen, which is after the Garderborgbakken, which is visible for vehicles coming from Finland. So the system is very modular, so it's fully possible to extend it to publish to the Interchange or other sources for distributing the data. We have the mechanisms to do that, but we haven't defined the specific telegrams to be used. This is still running, but some of the data sources aren't delivering anymore. So now I'm going to talk about slow and stationary vehicles. That is only available in sensors available in Garderborgbakken. There are 2 sensors that have been used. ITS perceptions cameras, which are located at the top of the hill and the bottom of the hill, and Q-freeze sensors, magnetic and radar sensors. ITS perception can spot vehicles coming in both directions, both from Finland and to Finland. Q-free only detects vehicles driving to Finland. That's also the most critical direction because that's going uphill in this troublesome hill. The image that you see here was actually the night after our tests, and the weather conditions deteriorated, and a vehicle actually broke down, and I had a message the next morning that there had been a stop. So this is a picture from an actual situation that occurred. The system was also implemented in Node-RED. It was a bit more complex because we had to log some additional data. We logged a lot of image data to verify false positives and negatives. That included logging images every 10 seconds. So Christian has been complaining that I have filled up the disk. And we also collected images if there was a notification. So if either Q-free or ITS perception detected that the vehicle had stopped, we logged the images for a few seconds. And they were also the images were referenced from the event in the database so that we can easily verify that there was indeed a vehicle that had stopped. We used JSON messages over MQTT to send notification. JSON is JavaScript object notation. It's a format very similar to XML. But it's more human readable. It's more compact and easier to use. MQTT is a message queue that I described a bit earlier. The data coming in is then interpreted by the system and sent to the correct application so that it can notify the operator. So we had a separate screen for slow vehicles and a separate screen for stopped vehicles. So when a notification that a vehicle stopped appears on the screen, or a vehicle has moved slowly, the operator has to go and verify that that is the case. And then if that's the case, the operator will send a notification and set the size, or set the size. You can do either. And the notifications are sent to Aventi system. They have a REST API that we could pass messages to. If Aventi receives it, it will display on their maps, and it will also be sent to ITS Perception, One Traffic, for display in their mobile application. And they were also sent to the Interchange and displayed on the map, showing messages, relevant messages from the Interchange. In this picture is from the actual test. You can see that we have a set assigned to state that a vehicle has stopped in Gardermobakken. This is from Helligskogen, which is a few kilometers from the hill. The data is not reliable enough to automate notifications, so we need human interactions to do this still. So this is the architecture as reported. This is quite close to how we actually did it. As earlier, I was mainly involved in the roadside system and the application backend system. So the two vendors collected data and shipped and sent data to us if there was events. We had 3 events. We had stopped vehicle, slow vehicle, and just vehicle passing. So we had the possibility to debug the system to see that it was live, that we were receiving information as cars were passing. It's quite good to have some sort of keep alive notifications, and the vehicle passing are good for that. Yeah, they sent that to Andeby, our application server. The data had to be handled there visually by and notifications were sent to the Interchange and to Aventi. So this is an ideal situation. The 2 arrows here aren't really there. They would go something like this in the system that we implemented. That's because we didn't have any consumer that could receive the data. And the images were set directly to Trojana. So in this is both for the weather data and for the stationary and slow vehicles. This top level was not really involved. It was just mocked by the application running on the server. So this is an image from the actual test we did in October last year. So in the image here, you can see a vehicle has stopped in the going downhill. So unfortunately, this is not the case that Q3 would pick up due to their sensors will be in this lane going uphill. So we have a couple of notifications that a vehicle has stopped. and the operators have sent the message. And so you can see on this sign that the message actually has been set. This is an older picture, so that's probably not updated. And if you can see here, you can see this is from Aventi's application. You can see that a broken down vehicle image or icon has been set. It's set a little bit off the road. That was just to make it a bit more clear that the message was there, so that it wasn't superimposed on these other icons here. So just to make it a bit clearer. So this was a live test where we showed that eye perception picked up that the car had stopped. This message was sent to the backend server. It was interpreted by the operator. The operator sent the message, and the message was distributed to the consumers, which in this case was Aventi and the users using one traffic's application in the area. So that we demonstrated the full value chain. So just a quick overview of the data flow. You have messages flowing over MQTT to our server Andeby. User sees these notifications and send the commands either to set signs, which goes through the Triona system, or to notify using the Interchange and Aventi's platform. So this is what the system looked like for the operator. You have images of the relevant message signs. At this moment, the one at Perskogen wasn't operational, I think. So this is just to verify that the signs are actually set. The notification will appear in this top area, so the latest one will appear here. So if there are several notifications, messages coming in, the most recent one will be showed here, or the most recent one and the most important one. So if the most recent one is a stopped vehicle, and that will stop showed here. And then the operator can just have a look at these images to verify that indeed there is a car stopped. These will update every 10 seconds. So if a car is in the same spot for several of these images, you're pretty sure that you have a situation. Then you can choose to set the signs and or publish to Aventi and to the Interchange. And you can also ignore it if it's not a real situation. So very, very simple, but quite effective application. So some main takeaways here. The system generated a lot of data, especially the stationary and slow vehicle. We need to verify data quality for the situation detection, especially for false positives and negatives with regards to stopped vehicles. And that involves looking through large amount of image data, terabytes of image data, and match it with notification. So that's a huge job that hasn't been started yet. And we also need to verify that measured weather data really constitutes as severe conditions. Not necessarily that cold conditions is dangerous. There has to be a combination of conditions. So it's currently not safe to automate the notifications. We need an operator in the loop. If we chose to automate this, we would have a lot of probably have a lot of false notifications to the users, which may decrease the confidence for the users. So that was very short put that part of the pilots.
Now we will focus on the services mobile roadworks and traffic ahead warning. It is Torgeir Vaa that will give us insight in these services. So Torgeir, you could join us now.
Thank you, Per Einar. My name is Torgeir Vaa, working for the Norwegian Public Roads Administration. As Per Einar mentioned, I will present two use cases, one on mobile roadworks and one on traffic ahead warning. Just start with the presentation. Is it okay now?
Yes, that's good.
Yeah, good. Start with the mobile roadworks. Short introduction. We have a lot of mobile roadworks on the road network, both in the summertime and in wintertime. The normal situation will be to put up a warning sign close to the road to warn about mobile roadworks ahead. And this sign is often a way ahead of where the actual work is taking place, because the roadwork is mobile. And even worse, as we can see in the picture here, there is not always a sign ahead of the roadworks. It could just be a sign on the tractor. And this may cause some serious risk situation. The test area we have used, we had planned to do the demonstration on mobile roadworks on E8 in the Skibotn Valley, but due to the pandemic, we had to change our plans and did the test on the road around Jonsvatnet in the outskirts of Trondheim. This is actually a service that could be demonstrated anywhere. The road around Jonsvatnet is a municipal road with a low traffic volume. This is the architecture, similar pictures that Kenneth has shown. We could either have used the ITS G5 technology or a cellular network. We, of natural reasons, we landed on the cellular network. We don't have any G5 stations, roadside units around the Jonsvatn area, so we had to rely on the cellular network. This is another way of showing the flowchart using a cellular network. This will be described more in detail in a video following this short presentation. Just a few words about the test setup. We did a test in midsummer, used a cellular network, and we had a maintenance vehicle, car A, with a warning light on the roof. It's a light beam, including technology to send out information about speed and location. When the light beam was turned on, there was a signal sent via the cellular network to a cell phone in the following car, a car B. Now we will hopefully see a short video.
Mobile roadworks causes changes in normal driving behavior in and around the roadworks area. This will affect the driver and possibly lead to unsafe traffic situations and, in worst case, severe accidents. A solution to avoid these situations is to utilize existing cellular technology to warn road users in advance about nearby mobile roadworks. During roadworks, the maintenance vehicle sends messages about its position to the road operator's backend system. The messages are forwarded to the NordicWay Interchange Node. Service providers, such as car manufacturers, subscribe to get the messages from the Interchange Node. Drivers in approaching vehicles will receive warnings about roadworks ahead from the service provider's backend system. The message is communicated to the driver in the vehicle. Roadworks warnings allow the drivers to adapt their driving behavior when approaching and passing roadwork zones. This will help to reduce the risk of collisions and other accidents as a result of increased alertness and better traffic flow.
That's good. And then we have a similar video on the traffic head warning service.
Large traffic volumes and slow-moving vehicles often cause queues on the roads. Slow-moving traffic can lead to dangerous situations and accidents. This problem can be solved by utilizing existing cellular technology to warn vehicles about slow-moving traffic ahead. When a vehicle is moving slowly due to traffic jams or other incidents, it sends messages about speed and position to the backend system of the service providers, such as car manufacturers. The messages are forwarded to the NordicWay Interchange Node. Service providers subscribe to get the messages from the Interchange Node and distribute them to approaching vehicles. Drivers receive this warning on their mobile devices and get the opportunity to adapt their driving behavior when approaching the slow-moving traffic. This will lead to better traffic flow and reduce the risk of rear-end collisions and other dangerous situations.
Good. And I should mention that it was Per Einar's son who is the actor in those two movies. He was a summer student here at our premises. Now we just continue with a very short presentation of the traffic ahead warning service. The same test area around Jonsvatn, road around Jonsvatn. Similar architecture. Here we also could have used the ITS G5 if it was available, but we also here have used the ITS or cellular network. The same flow chart. Those two services are quite similar actually with the same technology. The car moved very slowly. Car A acted as a slow-moving traffic by driving way below the speed limit. And here is also the signal position and speed transmitted to a cell phone in the following car. Lessons learned very shortly. And we are quite dependent on that the cellular network works well and we have a good and stable signal. There will be a problem in some areas with poor coverage of the cellular network, and it can be hard to distribute a continuous location signal. It could also be a problem with sending out messages when the vehicle's OBU, onboard unit, is changing base station, and there could be a short period without any signal. So just to end up with a question: how do we overcome the infrastructure barriers hindering some of the CITS services to be used also in rural networks, rural areas? So this ends my presentation.
We will now go into the activity readiness of infrastructure for connected and automated driving. Now we change in some way the technology and move into more shortwave technology. But first of all, we will hear about Nordic Tour, that I will say is a world record in both length of corridor testing and collection of data. So once again, welcome to Thomas Levin, and I'm sure he will have some interesting findings to present to us.
Thank you, Per Einar. So I'll be presenting on the topic of the Nordic Tour, which was, as Per Einar said, a really long drive in the Nordics. The map you see on your left shows the complete tour. We had to split it into two parts, but I'll get back into that. The tour started in both cases from Gothenburg, went down through Denmark, across Sweden, over with the ferry over to Helsinki, around the Helsinki area, then north to the E8 and the Skibotten Valley, and then down south again. And the second part started in Gothenburg, cut across Sweden and went up the E4 towards the Finnish border, where the plan was to go around the Norwegian part once more. But due to the corona situation in March, we had to return halfway up Sweden. The good thing was that we managed to get enough telco data, so we have comparable volumes of telco data in Finland, Norway, and Sweden. Setting up such a data collection scheme is rather hard. Both Christian and me spent a good couple of days at the factory in Gothenburg getting the vehicle ready. There is a lot of details in getting the data collection to work. So just getting the signal from one small antenna on the roof required 2 Volvo engineers and 2 MPRA engineers. The picture also shows the Nordic Tour. It became the days were quite long. The beginning, we started from Gothenburg at 5 a.m. in the morning, and this is Christian outfitting the car on the right-hand picture with the NordicWay logo. And inside the car, we had plenty of PCs and logging equipment running. In the beginning, it took us close to 3/4 to start up all the systems, while at the last part, we were down to a good 20 minutes to 15 minutes. So the long trip around the Nordics was based on the idea that this covers most of the trunk road networks, the best kind of roads we have in Finland, Sweden, Norway, and Denmark. But being the best roads in each country does not mean they can be directly compared. If you take Sweden and Finland, for example, the roads are quite straight, even though they are a bit narrow and they have winter conditions. If you come to Norway, you'll be using your steering wheel a lot more. In total, it took us 120 hours of driving, split up into 2 trips, and in total, I think it was 9 days of driving or 10 days of driving. It's about 6,000 kilometers, and it included 3 border crossings while driving. The other border crossings were done on ships sailing across from Sweden to Denmark and from Sweden over to Helsinki. So there we have no data on the actual border crossing. The scheme that we have sort of developed in Readiness for Automation looks into what kind of services do road authorities have to make sure exist for vehicles so that we can get the benefits of automation, I mean. And basically we've boiled it down to 3 topics that we need to take responsibility for as NRAs, that they work. Not meaning that we have to create these systems, but we may have to enter into a dialogue with other public authorities to make sure that these systems function well. The first one is positioning, finding the location of the vehicle and being able to use the map data in relation to the location you find. So a key component for either CITS or automation is global navigation systems, satellite navigations, GPS, and so on. These systems have to work and they have to have good performance, and they also have to be robust in relation to unwilling or intended attacks on them. Then we have the community. We see that both CITS and automated drivers need to be able to communicate and send data back and forth through the cellular network. So it's important for us to check the quality of the cellular network. And the last part is that we believe that the automation will not come overnight. It will be a period with both human and machines driving vehicles. Hence, we'll have to have human-machine readable infrastructure. The equipment in the vehicle was set up to log all of these 3 areas. We had an industrial PC that was connected to the CAN bus and the FlexRay bus of the vehicle to extract how well the vehicle understood its surroundings. We had a highly specialized PC and equipment linked into the telco system of the vehicle to extract the performance of the in-vehicle systems. We had a tablet to monitor sort of third-party systems that might be mobile phone or tablet-based applications in the vehicles. And we had the last solution where we used a low-cost industrial modem to access the telco networks. All of these data sources were then piped into a logging platform that we developed and is available on GitHub. It's basically a lot of open source components linked together, so it's not a big issue. But the key thing that we did, and we're happy that we did, is that we decided that all data should either be able to join on both location and timestamps in the data collection. And we had some minor hiccups, or they could have been major hiccups, but thankfully, since we're able to map on both time and location, we were able to recreate the missing data during or after the trip. So for the infrastructure part, we mapped out the lane markings and the speed signs using state-of-the-art in-vehicle systems, ADAS systems at the moment. Then the cellular network, we had an in-vehicle modem, the one with the shark fin antenna on the roof. Then we had the next generation modem equivalent in the back seat. And we had a table in the front seat and an industrial modem in the boot of the car. And we also logged the GNSS signals using a u-blox M8 satellite receiver with full debug mode. So we are able to go back and look at the reception and the quality of the GNSS signals. The tour was split into two parts. For the telco systems, it doesn't really make sense to repeat a trip because there's not much difference. There might be some difference due to the utilization of the networks, but we don't believe that winter and summer or winter and autumn make that much of a difference. But what makes a difference is for the infrastructure readiness reception area. So we needed to check that that actually worked. But once again, the pandemic made it a bit harder for us. So we got halfway up Sweden before we had to return. The good thing is that we actually managed to get enough data in Sweden so that the results from the cellular networks are directly comparable between Norway, Sweden, and Finland. So we are quite sure we managed to capture enough data for our analysis. That being said, we also tested a service in the NordicWay specifications. This was the road and lane closure. This is a service that all nations, all 4 nations, currently send out through their DATEX nodes, their national access points. So what we did was to pipe that data into the interchange and then from the interchange onto a map so that we had all of these roadworks data available to us while driving. The picture you see on top is the cell phone with the application, with the map and the roadworks running. I believe this is a map somewhere in Sweden, I think, while testing. The vehicle was, I say, always connected. There are a few dropouts when driving on the cellular connections, but using normal HTTP protocols and reloading the web page, the problems were not really big. So we were able to get information on roadworks ahead continuously throughout the tour without worrying too much about them. And also the messages on the DATEX nodes and the national access points, there are quite a lot of messages available, but we selected the safety-related traffic information messages. And we also in Denmark extracted the speed and reduced speed sign information. So they have variable message signs with speed reductions on them, and they were also sent to the interchange. So when driving on the ring road in Copenhagen, we were receiving the speed limit signs in the vehicle as well as seeing them on the signs outside. The picture on the right-hand side is actually a sort of a proof of concept. The car is at the red dot on the cell phone, while the sign is also marked at the same spot. And we have plenty of these pictures showing that we can actually see the roadworks where they were marked in the maps. But of course, there are issues here as well as in any of the other applications, and they're mostly related to data quality issues. With the lane closure and road closure data, it was typically 2 conditions that we had: either ghost roadworks or missing roadworks. A ghost roadwork was defined as one that exists in the digital world, but when we arrived with the vehicle to the site, there was no trace of any activity in the real world. Missing roadworks, they were sort of, they exist in the real world, so we enter a work zone, but there are no digital messages about them. In Norway, we had several issues with these large and long roadwork zones. They were actually missing from the application. So we had issue south of Mo i Rana, between Mo i Rana and Mosjøen, where there was a 27-kilometer long roadwork that was missing from the national access point in Norway. So there might be some issues there. Then we had some interesting issues. Denmark are quite good at putting in roadworks that will appear ahead of you in time. And we were a bit too hasty when designing our filters, meaning that we got roadworks placed on the map that would occur later. So one also needs to make sure that one knows that if the data presents the current state that you're receiving, or if it represents some state in the future. Yet again, the datex messages are the same and standardized, but the procedures are slightly different in the 4 Nordic countries. So it was clear for us from this testing that we did in the 4 countries that using the interchange as a delivery mechanism works really well, but there is a need to work with harmonizing the processes of generating the data and how the data is, or the validity of the data. Are you exposing just at the current time, or are you presenting something in the future? So I think the conclusion is that national road authorities have a job to do here to fix these issues. So those were the road messages, closed messages, but also to prove that we had some live messages streaming in. We've talked a lot about the weather in Norway during this session here, but also in Finland. So it started out with the picture on your left-hand side, heavy rain cover coming in with lots of sun in between. And the radio was screaming in Finnish, and even though we've done some work with the Finns, we were never able to understand what the RDS TMC messages were all about. Then in our app that we had in the window, we suddenly got a message. It says environmental obstruction. We're still trying to figure out what environmental obstruction could mean, but we understood that there is something happening ahead of us. And on the picture to your right-hand side, you can see there's water in an underpass. There is heavy flooding in the underpass. So I think we have to apologize to Volvo for taking their car for a swim. It was somewhere in 20 to 15 centimeters of water in this underpass. So this was a message that was pushed out by the Finnish TMC and that we received in our vehicle on this tour around Finland. So it actually worked and we got the message in due time, but since we didn't understand what an environmental obstruction was, we did not make a good choice to detour around the site. And that's also something one should think about these services. They are very specific about the problem that they detect, but what you should do with the problem messages are a bit less helpful, to put it that way. It might have been better to receive detour information instead of an environmental obstruction message. So that concludes the part on road and lane closures, and then we'll go a bit further into some of the findings in this readiness for automation. One thing we had an issue with was that we were monitoring interference with the GNSS band, or basically with the GPS band. At the time of the Nordic tour, the conflict in Syria was blossoming, and the US deployed reinforcements. And during this stage, they actually bumped up the signal power on the L1 GNSS band. So we can actually see that the receiver had higher quality satellite reception during the days in Finland. And it's quite clear that there is something happening when we arrive in Finland and the day we are sort of exiting Finland. It's not about Finland, but it's actually about the Syrian war and how the US manipulates the GPS system. So basically for us, the issue here, we don't believe it caused an issue for us. The Norwegian national mapping authorities could see the same at their observing stations in Norway, but it sends across the point that we have to be aware that we are maybe using a system that we do not have any control over or can assert any control over. It might be better with the Russian, or not the Russian system, but the European system coming up. And there's also a Russian system. So you have some sort of redundancy, but navigation is mostly based on GNSS. So we have no guarantee using these systems. We monitored the GNSS, the error rates produced by the unit itself. How bad is it at guessing its position? It has a lot of advanced filtering algorithms, so it sort of tells you which locations were thrown out of the ones it calculated. On average, the median was under 1 meter in this internal offset of the system. But if you go to the column named maximum here, you get an interesting number in Norway. You're about 4.3 kilometers away from where you believe you should be, according to the GPS. And what we did was to look up where these issues happen. Where do you get these crazy GNSS error rates? And they're typically along the routes where we have tunnels. And just to say that, Norway has 1,295 tunnels, so it's a rather big issue for us. In Denmark, we're sorry we got a little bit too little data because of a defective USB hub that turned off our receiver, but that's something that happens when you're doing large-scale testing. But all of this was tested using consumer-grade GPS and should work rather well. Is GPS jamming fiction or is it a fact? This is from when we were passing Mjøsa, and we can actually see that we were jammed by this black truck ahead of us. What happens is that the indicator of GNSS jamming, the automatic gain control dropped, and the error rates internally in the GNSS system increased. We found more places like this in Kilpisjärvi, Mo i Rana, and Trondheim also. So there are some pieces of equipment that deserve or disrupt GNSS reception. Cellular coverage. There is a significant difference between antennas on the roof and retrofitted antennas inside the vehicles. And it's rather large, but there are also some real differences based on the SIM cards and the subscription, and basically how much you pay for your subscription. So from an NRA perspective, I think we need more transparency into how the telco industry works in this area. Roaming, yeah, it works. This is a map showing the signal quality. Blue is 3G, green is LTE, and red is GSM 2G. And what you can see in Norway is there's a lot of 2G coverage, mostly in the tunnels, otherwise it's LTE. While traveling in Sweden and Finland, we were never, almost never, there are a few exceptions, put into 4G band. We're always shuffled down into 3G technologies. So there's definitely something going on with the SIM cards and the deals that the different operators have on roaming. Another picture showing basically the same here. You can see in Norway, you go down to Edge and GPRS about 3% of the time, while 96% you're in LTE. On the other hand, in Sweden and Finland, you can actually see we're quite a lot of time within HSPA, meaning 3G signal types. Reception, it looks basically the same with LTE. It's a bit more concentrated in Sweden and Finland, but that's probably due to the fact that we were almost always shifted into 3G, so there's less data available. Border crossings, always interesting. On the left-hand picture, we're crossing in from Finland to Norway, and it's possible to see that the handover occurs approximately 3 kilometers northwest of the border with Finland. And the handover is sort of followed by a short period, I think it was about 500 meters, where we had no coverage, and then we were handed over to the Norwegian cellular network and got very good coverage. On the Øresund bridge, the picture in the middle, we had the handover in the tunnel on the Danish side. So we switched to a Swedish cell phone operator in the middle of the tunnel. Yet again, in the tunnel, there is the system repeats itself. There is a short period of no connection, then it flips over to Swedish networks. But the connection there, or the break in connection, is really short. On the Svinesund between Norway and Sweden on the right-hand side, you can yet again see this trace. You have fairly good coverage coming from Norway, then it turns bad and no connection, and then it flips over to a Swedish operator. Yet again, this stretch without coverage is about 1 kilometer. But we also observed on the cell phones, 2 equal cell phones in the car, that one flipped over to 4G very quickly, while the other one stayed in the Norwegian telco network and 2G networks in Sweden for quite a long time. We believe that this may be linked to what the phones were doing, because one phone was streaming data from the map that came from the interchange, while the other one was sort of resting. Infrastructure readability. These are a couple of fun speed signs in Sweden. How do you interpret them? 30 kilometers, 40 kilometers. Then you have to figure out, look at your watch, figure out what time it is, and so on. These do not really work for digital systems. This is another interesting point in the northern part of Finland. It seems like the left lane is allowed to drive 100 kilometers an hour, and the right lane is 80. Yet again, we believe this is an National Road Authority hiccup. There is something wrong with how these signs should be placed. More care should be taken on these processes. And of course, we can have fun of the Swedes and the Finns, but the Norwegians aren't any better. This is a work zone in Trondheim. You can see a traffic light on your right-hand side, that's red. And then you have a double yellow line on your left. So when the sign turns green, you'll actually get a fine of 420 euros for crossing this yellow. So I think yet again, it proves that the automation sending the messages, that actually works, but the processes on the national road authorities lack a bit at the moment. Other observations, we found 35 stranded cars along the road. None of these cars were actually on any of the interchanges on any of the Datex feeds in any of the countries. So there is probably either it's intentional to leave this data out, or there is a lack of good input data to NRAs to publish this kind of data. Yet again, we need to look more into the processes. Automation requires coherence between the digital and the physical work for it to work well. And it's time-consuming to do the analysis. We've collected about 200 gigabytes of data and are now on the final stretch of analyzing this data. And then I think I actually used a bit more than my time, Per Einar.
Yes, but it was a very good presentation, so that's okay. We will now move into the short-range communication technology. But an introduction, we will go back to Jorunn, and she will have a short presentation on how to collect and analyze data that could be used as input to the service in-vehicle speed limitations. After that, the company Aventi will present their work with short-range communication. So, Jorunn, you can start your presentation.
So, welcome to Patterø again. This is the problem. We have queues built back on the motorway, and there is a shopping center and big workplaces that gives a lot of local traffic in the intersection. This blocks the traffic from the exit ramp. And this is a 2-lane motorway. And we see the slow-moving queue is building up on the shoulder. And the speed limit is 110 kilometers in summer. And this can obviously lead to dangerous situations when some drivers proceed to the exit in the right lane, in this situation, the middle lane, and slows down to or stops to join the queue on the change. The map from Google shows typical traffic on a Thursday at 8 in the morning. This was the normal situation before March and COVID lockdown. And the queue can build up past the information signs 1,000 meters before the exit. As a solution to this, we can use variable message signs to warn oncoming traffic about the situation, or send denim messages to the vehicles. In-vehicle speed limits or queue warnings would be a more flexible solution to increase traffic safety. The speed limit in the area could be reduced before the situation escalates while the queue is building up on the ramp. In-vehicle speed limits would be ideal in this situation, and while we are waiting for vehicles that can receive the messages, we have been working on the detection of queue and the content of these messages. Reference systems for queue detection with inductive loops are installed, but we have not been able to calibrate them yet because of lack of queue after the COVID lockdown. The queue are back now, but it is more unpredictable when we can find it. We have worked on a method to detect the back end of a queue based on information from the vehicles. These can be ITS-G5 COM messages giving position and speed. This box plot shows the speed of a vehicle approaching the intersection from south and meeting a queue. The roundabout is at the left side, and the shaded area on left is part of the exit ramp. The dotted line shows vehicle speed on the ramp in a free flow situation. The road is divided in 50-meter sections. Each box shows the speed on one section. The back end of the queue is very clearly visible as the box with the highest speed variation. A positive side of this method is that we don't need to track the vehicles through the intersection. All that is necessary is speed and position. Information from several vehicles in the same road section and time frame can be grouped together, and the calculations can be done in roadside equipment. When the traffic is low, the information passed on can be no queue, There is no need to pass on information of speed from a single vehicle. To prepare for in-vehicle messages, we have performed a lot of tests of the ITS G5 radios to gain an understanding of the challenges we have to take into consideration when deploying this technology. The image shows the difference in coverage with different heights of the roadside antennas. The red dots is 1 meter and blue dots is 7 meter. We see small variations in topography can give big differences in radio coverage. For example, north of the intersection, the range is much shorter on the northbound lane than on the southbound. Other tests performed have focused on range and the influence of topography, height of antennas, and shadow from other vehicles in heavy traffic. We would like to thank Aventi and Q3 for the collaboration on this test site, and we will continue testing to learn more about the challenges and possibilities of this technology. Thank you.
Now we will say welcome to Aventi, who will have a longer presentation on their work with G5. Yes, it looks fine.
Yep.
So we can start.
Here we go. So this is the E8 Borealis CITS testbed, and basically what we did here is we installed some ITS G5 radios here in Garderborbakken, so that's like a Wi-Fi hotspot for vehicles, and the rest of the area we covered with regular cellular communication. So that was one of the goals with the E8 Borealis, to test hybrid communication. This is the hardware that we provided. We have two Q3 roadside units. We have two mobile roadside units based on Corda equipment, and then one regular Corda roadside unit. We have 4 Q3 onboard unit with Android display. We rebuilt these. Basically, we took out Ola Martin's electronics and put it in this black box here instead of this white box, so that we could get access to the USB port and things like that. We have 10 old Capsch onboard units. They are built in Jönköping. It's a discontinued product, but the Norwegian Public Road Administration purchased these a long time ago, so we included them in the project. And then we included one Corda onboard unit. Here is the architecture for the system. So we have this Azure virtual machine running here, all the services in the backend. Right now it's running in Netherlands, but maybe we can move it to Norway now that Azure is also providing data centers in Norway. So here we have an onboard unit, which is talking to this roadside unit using the 5.9 gigahertz ITS G5. Do you actually see my arrow when I point like this?
Yes, we can see it.
Yep. Yes. And then we have the onboard unit, which in this project support CAMDEM, IVI, and SAM, and they can also communicate directly using the cellular network straight into the MQTT broker. So either the vehicle is communicating via the roadside unit and then MQTT, or it's communicating directly by itself with the MQTT broker. It's also possible to run the Android app in standalone mode, and then it will talk to the MQTT broker. Then we have some options down here. We can plug in an OBD dongle. We can buy it from Kjell & Co. or Claes Olsen. It's $350, and it has a Bluetooth interface which talks to the onboard unit, and then again via MQTT to the backend system. We also tested the solution with OEM's APIs, in our case Smart Car, where we can get the same information as the dongle, just straight from the API into our Android app and back into the MQTT broker. The MQTT broker makes the data available in MongoDB, so Thomas and them, they can connect to the MongoDB and create queries if they want to. The data is also available through a regular API here, and there's the web interface that Ragnhild and Jorn talked about. As part of E8 Borealis and E6, we also made an interface to the Datex server, where some of the messages will show up in the Datex. I'll show more about that later. So to provide the coverage using the cellular network, we created these virtual roadside units, and software was provided by Yukogu. We placed them in different quadri tiles. You can Google it if you want to, but that's how they slice up the maps. Both Bing Maps and Google Maps and all the map services slice up the world in different tiles. Right now they are sitting in these tiles here. So this map tile here, 1200, is covered by this virtual roadside unit, and this tile here, which is 1022, is covered by this roadside unit. And then we have the regular physical roadside units sitting here. The way the hybrid communication works is the traffic management center, in this case the central ITS server, will transmit all the messages both to all the physical roadside units and to the virtual roadside units, and the vehicle will receive both. And then it just picks the most recent one to display for the driver. And the vehicle in turn returns its CAM messages. I didn't show that in this figure, but it returns the CAM messages both through ITS-G5 and the MQTT and back to the backend system. In addition to test out hybrid communication, which combines short-range and long-range CITS communication, we wanted to test out service announcement messages. This has been part of the ETSI and ISO standards for several years, but very few projects have looked into using them. So it's a very simple concept. The SAM message is an empty box where we can put in our own traffic services. So in this case, we can initiate a SAM message. It could be signed by a certificate from the EU CCMS. We have not done that so far in E8 Borealis. Then we bundled up the SAM message. Here it tells you where the URL is for this service, and this is the application ID, the ID number for the application running in the onboard unit. And then we transmit it either through the cellular or the roadside unit to the onboard unit. Once the SAM message enters the firmware stack, the firmware stack will check which ITS AID it has and send the data to correct the program. If the program is not present in the onboard unit will download the program and then execute it. The program, in this case, if it's travel time, will it's like a stopwatch with a start and finish line, will calculate its travel time and send the result back to this service. And the other case we had was a border crossing. So if you're crossing into Finland, from Norway to Finland, then it'll start subscribing. The onboard unit will stop subscribing to the Finnish MQTT server instead of the Norwegian MQTT server. Here's a video where you can learn more about it. This is the E6 Patra and a continuation of what Joran just talked about. So we have implemented two functions for these RSUs. One function is queue detection. So if there's a lot of CAM messages here, and all those CAM messages are indicating a slow speed, then the roadside unit will trigger a DEM message for traffic congestion. On this exit ramp, if there's a vehicle moving in the wrong direction, the roadside unit will monitor these CAM messages, and it will detect that the vehicle is moving in the wrong direction, and it'll send out the wrong way driver DEM message. This is the hardware that we delivered for the E6 Patra. It's lots of CODA equipment. We have 4 CODA onboard units, 4 CODA roadside units, and then we have 42 CODA onboard units. 2 of those blue onboard units we turned into mobile roadside units. They have a big lithium battery here, which lasts for several days. The rest, most of the time we've had it hooked up in a rig in our lab here to test a lot of traffic with CAM and DEM messages when we develop our MQTT communication or backhaul solution. This is the system architecture for E6 Patra. It's a subset of E8 Borealis, and it only has one communication channel. It's the 5.9 GHz ITS-G5, the short range, with the MQTT backhaul to the backend system. And then hopefully we'll get one of the Golf 8s to visit E6 Patra, because it has built-in CODA hardware that can communicate with this CODA roadside unit or any roadside unit. As a side note, Q3 has also mounted a couple of their roadside units in the E6 Patra intersection. So we have our own little continuous plug test going on. So that's very interesting. All those onboard units, we took them down to Rygge Airport. The NPRA had borrowed the airfield to do a test where we were transmitting messages at high speed, big messages. We had some custom-made messages. We called them raw messages. And then we drove past back and forth here to see how many packages we would lose. So this would simulate heavy traffic on the road and congestion, and then we can see if we can actually receive all the messages from the other vehicles. So SINTEF and the NPRA and Q3 are working on the data that we collected, and they can provide you with reports from this test. It's very interesting. Now it's Thomas' turn.
Thank you, Bjørn Magne. So seeing that the Potterø test site was set up, we wanted to see how we can utilize these vehicles that are sending messages. Could you flip the slide? Thank you. Our problem as a national road authority is to know what's happening everywhere on our road network. It's rather large and it's kind of hard for us to do so. And the traditional sensors typically give you a slice across the road at one specific place. But seeing the pictures of the Golf 8s transmitting messages in about 500 to 1,000 meters range meant it would be really interesting. So we decided to test, could we use the Potterø intersection to harvest the CAM messages and produce wrong way driving and Q spillback. So Jorunn has presented you with the findings on using vehicle speeds from GPS positions, basically using the CAM messages to find the back of the queue, and that works rather well. The other thing we tried to do was then just to sit down and wait for the first Golf 8s to pass the intersection. Well, we are still waiting, so flip the slides, please. Basically, it's radio silence. For some reason, Norway is, or there is a reason why Norway is not a member of the European Union, but we are still a member of the European Economic Area, which means we follow the same laws and regulations as the other EU countries. We just don't have the right to vote. And we talked to Volkswagen what actually had happened. And what has happened is that Norway has been sort of shut out of this ITS-G5 due to legal issues. So there is basically a geofence guarding Norway that turns off the ITS-G5 radios in the Gulf when they arrive into Norway. The reasons for excluding Norway was that they had not done the legal work in relation to the use of radio frequency, privacy, GDPR, and data storage regulation. We've talked with our national frequency authorities, and they have confirmed that, of course, Norway complies with the same EU regulation, and also Q3 is a large company producing radios in the ITS-G5, and they are in Norway. And the GDPR regulation, we also have confirmed that we follow the same EU law. So then our goal was to see if we, in the future, it's not going to be part of the NordicWay2 project, but we'll do it anyhow, is to figure out, can we negotiate with Volkswagen to get them to turn off their radios and design some tests for us in Norway, because we want to see what the messages from the Golf 8s look like and how we can use them. So we have a big thanks to our suppliers, both Aventi, Q3 and Coda, who actually managed to get the NPRA into a dialogue with Volkswagen on the aim of doing testing and ultimately turning off this geofence so Norway gets the same traffic safety equipment that the rest of Europe has. It's rather ironic that the best class or the best student in the class in relation to traffic safety has had traffic safety functions actively shut off. But we're looking forward to the work with Volkswagen. Then back to you again, Björn.
Yes. So we had some meetings with Volkswagen, and we agreed that we'll first go down to Wolfsburg, bring our equipment from E6 Patra and do some testing. So we'll have our centralized test over here in the backend system, sending them messages to our mobile roadside unit and see if they are picked up by the Golf. So then we have to make sure we have matching PKI certificates. And the other way around, we'll see if we can receive the CAN messages and display them here on this map. We will also simulate that we are a fire truck, special vehicle 10, and we'll transmit the CAN message 95.1, which is emergency vehicle approaching, and see that the Golf received this message, and also that the fire truck can see the Golf, and we'll show it in its display here. Next step is to bring the Golf to Norway, have them turn off the geofence, and repeat the test. Then we'll do the test in the actual Patra intersection, and we'll do the test with an actual fire truck, where we connect the digital output, or 24 volts or 12 volts, from the light bar on the truck into a digital input on the quad onboard unit, which will trigger the same DEM message 95.1. The Golf supports currently these DEM messages. So we'll test all these. And this is how the message will show up in the dashboard in the Golf. So here down at the bottom here in this picture, you see a emergency vehicle approaching. And here you see stationary vehicle, or maybe dangerous end of queue, I'm not sure actually. But we can test all these in the Patra intersection. Back to you, Thomas.
Thank you, Björn. Of course, they turned off the geofence in Norway, but luckily we have friends in Q-Free, and Q-Free are a multinational company, and they have some personnel located in Warsaw in Poland. So there we actually have them they turned on a radio in the window of somebody's apartment overlooking a main road in Warsaw. And there we actually could find, and we have confirmed that these messages come from a Volkswagen vehicle. And you can see it's rather detailed. You have the location, you have the confidence intervals, but you also have the high frequency container data streaming out of these vehicles, giving us if it's turning, if it's accelerating, if it's braking, steering wheel angle, and the either acceleration or retardation. And you also have some information on the vehicle, if the lights are on or off, and some more. So we're really looking forward to test to see if this can become a really good way of sensing traffic. Back to you, Björn.
Yes, I'll talk a little bit more about the detection systems that Joran talked about. In the Patra, we implemented the cooperative collision warning, or wrong way driver detection. So here you see the, I'll replay it. Let's see. So here we see the green ball here, that's the CAN message, and it'll kick these balls, which are the DEM messages, down to this truck here and into the backend system. Let's see. So basically what we're doing, we're just receiving CAN messages from this vehicle. The roadside unit detects that this vehicle is moving in the wrong direction, and then it sends out the DEM, warning other vehicles in the area, and also reporting back to the backend system and the DATEX server. This works beautifully. If you want to configure one of these, we call them detectors, wrong way driver detector. You simply click on the roadside unit in the map, and then you add a new detector here. So we have support for wrong way driver detector and traffic congestion. And then you just drive a geofence where you want the detection. And then it asks for a couple of other parameters like the direction and things like that. Okay, so looking ahead. We at Aventi, we envision one CITS platform for all road traffic services. So here we have an illustration. We have the traffic lights, we have all the CAM messages, the DEM messages, the SPAT and map for the and also the SAM messages and IDI messages here. And we also played around with CODA's locate using the V2X to locate vehicles inside tunnels, which works great. We have that installed in one tunnel. And we envision this will be a single digital European market for V2X. Putting equipment in vehicles, maybe we can put the transmitter on our kids when they walk to school. The phones would be included. We have the roadside units. We have radars that can detect old vehicles and send out CAM and DEM messages on their behalf. This is the camera from FLIR. We tried this one. It can see bicycles and send out the DEM message and CAM message on behalf of the bicyclists. And then, of course, we will rely on the 4G and 5G or 3G network in some countries to communicate all this data back and forth to the backend systems. Then we have a lot of service providers. We've been testing, we use the Norwegian Mapping Authority as maps. We use Google Maps. We use all the data that the NPRA makes available. We host our services on Microsoft Azure. We'll be using the IDNOMIC or the EU DG Move ITS PKI, CITS PKI. We played around with Smart Card to connect to the API of other vehicles. So all these are services that we use in our solution, and then we have all these businesses and organizations that might use this data, and that in turn will provide the better and cheaper services for all of us. Here is a list of pains that can be resolved by a common V2X platform. The first one here, that's road use charges. We think that it would be a waste to make two technology platforms, one for road use charges or dynamic road pricing, and then one for all the other traffic services. It should be on the same platform. Many feel unsafe when they're driving in tunnels and winter convoys across the mountains, so we can use VITX to provide them with assistance and help. Many trucks, foreign trucks in Norway cause dangerous situations. We can keep track of trucks. The traffic pollution is too high in Norway, so we have the possibility to make geofences. Q3 has done a lot of work here. In urban mixed-use traffic areas, we can increase the safety, like installing the FLIR camera that can detect pedestrians and bikes and send messages to the vehicles. It's hard to find public street parking for delivery trucks, craftsmen, and handicapped drivers, so we can make solutions using the service announcement message where they can order roadside parking in the cities before they drive into the city. During tunnel fires, it's hard for the firefighters to know where the accident is, the fire maybe, where people are located, vehicles and dangerous good vehicles. But using V2X, we can provide them with all this information. And then the National Traffic Management Center, they give good information for the main roads, but they don't give any information for the city streets. So we could use V2X to create virtual traffic management centers for all the different towns and cities and villages around Norway, where local authorities can put in their own traffic messages. The last hurdle, really, everybody agrees, yes, we need this, we got to get started. The last hurdle is that we have two competing technologies on the short range two competing short-range technologies. So all this blue stuff is pretty much in place, and they both want to snap in here and be the access layer to between the vehicles. So that's an ongoing fight. Here is an illustration. So we have the two short-range technologies on this side. Here we have the one that we've been testing so far in E8 and E6, and here we have the PC5, the competing short-range technology. And both these two short-range technologies will also use this long-range, which is basically using regular 3G, 4G, and 5G for long-range communication. So this one is pretty much set. It's just picking one of these two, which seems to take a couple of years to hash out. In the US now, they made a peace deal between the SRC, which they call ITS-G5, and the PC5 CV2X. So the deal basically is that they will split the 5.9 gigahertz frequency in between themselves and have at it for 5 years, and then they'll see who is the winner after 5 years, and then the other one will phase out its technology. In Europe, large-scale ITS G5 deployments are still continuing. So we have this organization here, which is just a couple of road authorities and other organizations that got together to say that we'll continue deploying until the European Commission decides which technology to go for. So right now they are installing 525 roadside units in Austria, or Aspinac. So that's my presentation.
We have now reached the end of this showcase. Hope you have found the day very interesting and that the presentation gave you good information on what we have done in the Norwegian pilots. I will thank you all for participating, and a special applause to those who have given us the interesting presentations. As I mentioned, the presentations will be available at the NordicWay.net website. So with this, I will close the showcase and wish you all a healthy winter, and hopefully we will meet again next year. So thank you and goodbye.